Yeah, so welcome everyone, and thank you for joining these presentations. My name is Su Wing, and I co-authors this paper with Dr. Bin Tran from Latrobe Universities. I myself I'm at the university in Australia, and our work is about online generative programming approach to dynamic production scheduling. So a little. This is outline of my presentation, some introduction, a little background about the problem itself, and also the motivation for why we're working on these methods. It's a very initial step, but we see something rewarding, and we want to share with everyone. I'm gonna talk deeper about the proposed methods, and we move to experiments, and I'm gonna wrap up with some conclusion and future work.
Going to the speakers. That's the problem.
Can you still hear me well?
Okay,
Hello.
get technical. Can you just message someone to get the technical?
Should I wait?
So everything is fine. We can hear you and we can see your slides.
Yeah, sorry, I just hear some background noises. I'm
Please
not quite
go
sure.
ahead.
Yeah, okay. With quick backgrounds about production scheduling, which is the areas I'm working quite closely with for the last for 10 to 15 years. This is my focus for the presentation today. I'm interested in this problem because it's addressed some practical challenge, and you can find production scheduling problems across different areas, including manufacturing, sometimes in logistics, and sometimes if we're clever enough, we also see this kind of application in service sector as well. And for production scheduling, there are different variants, including job shop, flow shop, and open shop, and also something more complex as flexible job shop. The challenge of solving these problems that are because first is they are combinatory optimization problems, and it's been proven to be hard. So finding optimal solution is hard, if not impossible. So the exact methods can only find optimal solution for small problems. But in practice, sometimes we also have the situation where we have interdependent decision makings. For example, when we need to release the job to the shop floor, and if we have a lot of job coming in, which one we should accept, or we have to solve problem with due date assignment as well. So there's a lot of challenging things there. And of course, for practical problems, then we usually have a lot of conflicting objective. And for this because it's work in the very dynamic environment, so dynamic changes and uncertainties are expected, and it's make the problem even more challenging. So there are multiple solution methods have been proposed in literatures. The earlier version of these methods are traditional optimization methods like mathematical programming, branch and bound, dynamic programmings. There's still quite a lot of people working on these traditional methods, but mostly they apply to static problems. Advanced optimization problems are also being used to develop the solution that work in dynamics environments. For example, rescheduling, proactive scheduling, but they tend to be computationally expensive, and it also require a lot of trial and errors to find the best settings for the algorithms. Heuristics such as dispatching rules or what we call some others reactive scheduling rules are also great in terms of speed, because it's mostly based on the local information and try to come up with a simple way like prioritize job using some priorities values. This can solve problem very quickly. It can work in dynamic environments, but they often criticized for their performance. And genetic programming in the last 10 years or so has been widely used to design highly effective dispatching rules to target production environments. So this is the frameworks. This is in one of the papers that we published a few years back, and it's for to apply genetic programming for production scheduling. Usually, we come up with we start with production is the production scheduling problem themselves, and we're gonna see in what way heuristic can be used in these problems. And next is that we try to break them down into smaller pieces and see which one to fix and which one we can optimize further. So that part, then if we already identify the part that we can optimize, then we're going to figure out, okay, what is the component required to help us construct that component in heuristics. So most time, our work is focusing on building the priority functions within the heuristics or the spectrum rules. So we're going to have the terminal set and function set, which is quite common in genetic programming. Use that, we build up the representation. And when we build the representation, then we're able to come up with populations of programs or rules. And we're going to evaluate using the traditional kind of GB's evolution cycles. And then we're going to rely on some evaluation models. Most of the time, it's going to be some simulation models, which we use to evaluate how good is our heuristics. The limitation of the genetic programming methods is that they're designed for offline learnings. Most times, we already have established simulation models based on our prior knowledge, based on our existing data. We construct the simulation models, and that can tell us something about the production environments, and we'll use them to test the rules, the heuristics generated by GB, and we use that to see which one is better. We use that to calculate the finished values. This approach is work well in our papers, in the literatures. They may not be practical in real-world application because the production environment itself can change rapidly. So, but thing is that when you work with such a dynamic environment, that changing if you look at that in machine learning, you can also think of it more like something like concept drift. So in this case, analyze, understand the environment setup, the simulation models itself is going to be the bottleneck. So there's some solution that we think about, and some things we also see in the literature. First is we can develop universally good heuristic or rules. There's things that require a number of attempts in the literature to try to go with this approach. But previous studies have revealed that a single rules cannot dominate in all scenarios. And that is what we see across multiple papers. Another approach is to learn specialized rules for each shop condition offline. So we come up with many different scenarios, and we train specialized rules to work on each environment. And when we apply, we just see what situation we're in, and we pick that specialized rule to apply. But then it's required problem domain knowledge. We need to understand about all possible scenarios and data to develop the accurate simulation models. Okay, so in these papers, our goal is to develop a new online genetic programming methods for dynamic process scheduling. In this case, we also have multiple decisions, and we have flexible operation. The domain we want to apply to is called flexible job shop scheduling. And these OGB or online GBs are different itself from the others through three main aspects. So first, we not assume any prior, we don't make any assumption about the environment, so we don't have any prior knowledge about the environments. We work on the competitive populations, so they compete each other to try to see which one should be applied in certain situation. And we try to come up with an adaptive evaluation. So when the online GPs is working in the environment, it's try to adapt itself and depend on what is observed. So something quite similar to the concept of reinforcement learning. So to break it down, so we try to develop new adaptive model to evaluate generated scheduling rules in dynamic production environments. We try to develop new reproduction process that allow our proposed method to explore competitive scheduling rules efficiently. Because if they compete and we have maintain very large, huge population, is going to be quite unstable. So we need to come with a way that make things go smoother and more efficient. So we also design mechanisms that allow all online genetic programming to escape from local optima without destroying useful genetic materials. It's challenging in the offline scenarios, but now it's for online application, it is even harder. And we also want to come up with a method to select potential rules based on the estimate fitness and size as well. Okay, so a little bit of introduction of the dynamic flexible job shop. So this is going to include two parts. One part is about routings and one part about sequencing. So imagine that you have a lot of custom orders coming in and you need to process them through different machines and deliver them when they are completed. So they're going to be the routing rules where we need to assign, okay, for each operation, each jobs, which machine going to process them. So in flexible job shop, you have the option to process a different machine. And after you determine where they're going to be processed, when they arrive, they're going to join a queue, and we need to determine which job in the queue should be processed first. So that we call sequencing. So
sorry to interrupt. You've got about 3 minutes left.
Okay, sorry. So for online genetic programming, then we go through loops and we maintain an archive of effective rules, and we apply from time to time, get the best fitness, and we try to apply the most competitive rules in each time window. For representation, we use traditional tree-based representation. And this is sketch showing how the fitness evaluate. It's mainly based on a machine learning model, small one, to predict the long-term performance of the rules and the immediate realized objective. We combine them and try to predict how good the rules are. We also apply another rules in the literature, including pre-selection, something similar to surrogate-assisted models, and diversification approach to make things less likely to be trapped in local optima. So for the results, we figure out that we compare with the existing rules in literatures, and we figure out that our online genetic programming perform quite well. If we apply all of them, then in the dynamic scenarios, then it starts very bad, but over time it's improved and is able to dominate all the existing rules. And we also compare that with other genetic programming in the literature, and we see that it's quite competitive against the quite of a surrogate-assisted genetic programming. Compared to the simple genetic programming, it's performed quite well as well. And one feature that's quite good with the online genetic programming is that we also quite maintain a quite simple, small size programs in our evolution. In conclusion, so that in this work, we introduce a new methods, online genetic programming, and we're able to help us optimize the scheduling rules on the fly. This is one that this work present the first successful methods for online methods to complex dynamic scheduling problems, but it's still at very initial stage. But it shows that it can outperform a lot of existing scheduling rules. It can evolve the rules that are competitive with the state-of-the-art offline genetic programming methods. There are a lot of more recent ones that have been proposed, so we got try to compare with those in our future work as well. And one thing is also quite encouraging is that we're able to produce very compact rules compared to other GB approaches. For future directions, we want to revise and further optimize the OGB. This is the first attempt, so it's a lot of things that we can do. We want to apply more advanced techniques like surrogate models to improve efficiencies. And we want to extend the framework to handle multiple objectives, not just a single objective like the one we show in this case studies, in this paper. And we also want to invest the incorporation of cooperative convolution to enhance the effectiveness and interpretability of the evolved strategies. Thank you very much.
Thank you very much for your presentation. I'll first take any questions from the floor.
So thanks so much for the nice talk. If I understood correctly, you're using GP to evolve the rules dynamically, but have you compared it with just evolving the actions dynamically? So, or using things like online planning methods like Monte Carlo tree search?
Right, right. That's a very good point. I think I have not considered that in this paper, mainly because the methodologies we use using genetic programming to evolve the priority functions is slightly different from the Monte Carlo's approach. And yeah, I just not consider that way, and I need to figure out a fair way to compare them as well.
Sure, sure. Okay, thanks.
Yeah.
Any other questions? I'm just going to quickly check if there are any questions online. Okay, there are no questions online. I just have one question regarding what the rules actually look like, rules that were generated. So if you had to look at them, are they at all affected by redundant code and bloat in GP? And how close would they be to rules that humans would typically generate?
Excellent questions. I think we do a lot of those analyses here on the interpretabilities of the rules in the offline genetic programming. For the online one, because they change quite rapidly. And they, as I mentioned, they compete with each other when they apply in the online settings. So it's very hard to actually understand how it's work. And but if you look at individual rules, then yes, if with the compact size, they inherit some good building blocks that we can easily see in existing scheduling rules.
Okay. Thank you. We have time for one more question if anybody has a question. Okay, if not, let's thank our speaker again and congratulate him again on being nominated for the Best Paper Award.
Thank you very much.
Just a reminder, the first 3 presentations have been nominated for the Best Paper Award, so please vote for your selection. Thank you. So we're on to our next presenter. Yes. You can take out the mic. So our next presenter is Ming Zhu, and I'm going to hand over to her.
No. Okay. Okay. Yeah, thank you. Okay. Hello, everyone. I'm Mo Xu, and you can also call me Nora. I'm very happy today to be here at Gecco 2025 to present our recent work titled Quality Diversity Genetic Programming for Learning Scheduling Heuristic. And this is a collaborative effort with Frank, Anata, and Yusong. And also thanks to last speaker, Buck, to have already given an introduction of the dynamic scheduling and also the genetic programming methods. And our work also use GP for dynamic scheduling, but differently, we try to solve a different aspect of real-world requirements. Now let's go into the motivation. Well, in real-world optimization, we not only need a single best solution, but instead we need a diverse and high-quality alternatives for adapting to some dynamic conditions. And this is where quality diversity or QD shines. So QD is designed to find a wide range of effective solutions. But currently, QD primarily focuses on static problems, and its exploration in dynamic combinatorial optimization problems is limited. And also, there is a theoretical gap for using QD in learning heuristic, which is quite different from learning the solution directly, because we have to search on heuristic space instead of solution space. And consider this motivation. In this paper, we want to address two fundamental challenges. So the first one is how we can define the behavior descriptor for a heuristic. It's not like other domain, like maybe we can describe the robot's movement as a behavior. But in our case, we have to translate the rule like TRS plus PT, this kind of abstract rule, into a meaningful behavior. So how we can do that? And another thing is that how we can define a fixed and a manageable map for this complex space. And another challenge is that how we can maintain and update the map in a dynamic environment. It's like in real world, sometimes the problem will evolve. So in this case, if the individuals or the heuristics are evaluated by using different data sets, how we can compare the heuristics and how we can efficiently update the heuristics into the QD map without re-evaluating everything, which will be very time consuming. And with these challenges, so our methods have the contributions. First, we propose a novel QDGP framework for the dynamic combinatorial optimization problem, and we use a dynamic scheduling as a case study. And secondly, we have a map building strategy which can link the genotype to the behavior. And this allows us to visualize the QD map for diverse heuristic discovery. And finally, we do experimental validation. We show how the map evolution and how the solution distribution during the evolutionary process. And we also show how the diversity is maintained in the QD map. And we test our methods and compare it with baseline methods on dynamic scheduling problems and both limited and enough training data. Okay, now it's about our method, qualitative diversity genetic programming for learning heuristic. So this table shows the functions and the terminals to construct the individual. So we have an individual like this structure. We also have a sequencing rule and a routing rule. And this table shows the parameters about the QDGP. Like we have a 500 as the population size, and it will evolve over 200 generations. And we also use the standard parameter like the crossover rate at 0.8. And this is the overall framework of our methods. So we start by initialize an empty QD map, and we also initialize a population of heuristics. And then we do fitness evaluation, and we also calculate their behavior. And then we update the QD map with the heuristic and based on their behavior. So this is the QD map building and the initialization process. And the core of the algorithm is the breeding loop. So we do parameter selection from the QD map, and then we breed to get a offspring, and then we do evaluation, and again, we calculate its behavior. And we directly update it into the QD map. So that is to say, each time a new individual is generated, we will directly update it into the QD map. So this ensures that we always reflect the most diverse and high quality map that we discovered so far. And in the end, once the stopping criteria is met, we will finally output the whole QD map instead of a single solution. So here we can see that the QD map is the key point. So how we can construct a QD map for heuristic? So we use what we call a three-base methods. So first we have a DFGSS instance, and we select for sequencing decision points with 3 candidates. And also we select for routing decision points with 3 candidates. And for example, this is the individual that we want to calculate the behavior. And this table shows an example of how to calculate the phenotypic characterization of the individual. Well, today I won't go into the detail, but if you are interested, you can follow this paper. So for the 4 sequencing decision points, we will get a 4-digit number like 2012, and we do the same for routing, and we get 2021 in this example. And we use the 3-base methods, so it will give us 81 possibility of both sequencing and routing behavior, which will range from 0 to 80. And for this example, we get a unique cell for 65 and 47. So finally, we can build a manageable QD map, and we can also show the individual in the map. Okay, so that's about methods. Now let's look at our test performance. So the animation here shows how the QD map evolve from the beginning to the end of the evolutionary process. And the GPF represent the standard GP, and the QD GPF represent our methods using the adaptive tournament selection. Adaptive here means that the tournament size is adjusted based on how many number of individuals we already find in the QD map. And another one is a hybrid selection, means that for half probability, we use the adaptive tournament selection, and the other half, we just use the random selection to further give randomness in select parents. And as we can see that the GPF, the baseline methods, only explore a small area of the behavior space. And compared to the baseline methods, both the QD-GP variants provide a very good coverage map, and especially the QD-GPF2 that give more randomness in parent selection has a more better coverage map. And yeah, I have to mention that the darker the color, the better the performance. So not only we improve the diversity, but also we find more areas that give promising performance. And we do further analysis of the QD map. So this figure shows the marginal distribution of fitness values along the x-axis and the y-axis of the QD map. And we found some interesting findings. So first, the routine behavior 27 and the sequence behavior 0 gives the best performing for this example. And we also found that the dominance of routing, like the variations in sequencing had the least impact than routing. And we also found the multiple distinct routing behavior, like 1 or 7 or 15 or 27, gave relatively better performance. And this actually suggests that optimizing routing behavior is more important than sequencing. So this also gives insights like maybe in the future, we can focus more on optimized routing. And we also compare the test performance of the single best heuristic we found in QD map. So by compare GP and QD GP, we found that on all the test 6 scenarios, we get significantly better performance. And same for the QD GPF2, we get significantly better performance on all 6 scenarios. So this again verifies the effectiveness of our QD plus GP framework. And we also compare QD GP with QD GPF2 and shows that QD GPF actually give slightly better or comparable performance and show that too random in parent selection will can promoting diversity, but sometimes might hinder the exploration of the promising area. And we conduct a more detailed analysis. This is about the mean coverage percentage and the mean fitness of the entire QD map, and also the best fitness of the single best individual in the QD map. So again, both QD-GP variants achieve higher coverage rate, and it's even in the end around 6 times higher than the baseline GP. And we also got better the whole QD map performance compared to baseline. And again, for the best individual we found in the QD map, we also get a significantly better performance. So this is the test performance and the limited training data. So what if the training data is enough? So the area that we have enough training data, we mean that for different generation, we can use different subset of data to do evaluation. And this is a popular strategy to improve the generalization ability of the heuristic. So in this case, if we want to use the QD-GP, we have to re-evaluate the entire QD map. But actually, especially for a larger scale problem, which will be dramatically time consuming. So how we can compare the individual that evaluated using different instances. So we use these methods. We use a manual rule to the normalization, and we also introduce a penalty factor to account for the general improvement trends. And in this case, we make it more fair to compare individuals that evaluated using different training instances. And again, let's look at our test performance and the enough training data. So this figure shows the coverage percentage of the QD map. Again, both QD-GP variants provide a very high coverage rate compared to baseline. And again, for the mean performance of the entire QD map, both the QDGP and the QDGP2 achieve a significantly higher, better performance. And we also compare the test performance of the single best heuristic in QD map. But this time, unfortunately, our QD-JP variants underperform the JP baseline. But we guess it is because we already use different training data for different generation, and this actually has can improve the diversity. So additional use of the QD maybe will disrupt the balance between diversity and converge. Yeah. So that's about our methods and also about the test performance. So to conclude, we have a QDGP method, and that's designed for dynamic combinatorial optimization problem and featuring a map building strategy. And also the key contribution of this framework is that we successfully achieved the shift of QD from searching on solution space to searching on heuristic space. And we have a map construct and update mechanism and allow we compare individuals that are evaluated using different training data, and we also allow effectively and efficiently update it into the QD map. And also finally, we will output a diverse and high quality heuristics. And we show the effectiveness of our methods on dynamic combinatorial optimization problem. It shows strong performance in data limited scenarios, both on entire QD map and also the single best heuristic in the map. And it also shows strong performance in data rich scenarios on the entire QD map performance. But it also has some limitation, like the single best heuristics performance with enough training data is not very good. So in the future, we want to further improve the method, improve the QD strategy to try to address the limitation. Okay, so that's about my presentation. And wait a moment, I'm currently working at Simptech in Singapore, and we are hiring now. So our team actually do not only research, we also explore real-world application. And we have a number of customers in Singapore that they require inventory and also job shop solutions. So if you are interested, you can join the job market this afternoon, or you can just contact my two boss over there. Yeah, thank you. And now I'm happy to take any questions you may have. Thank you.
Thank you. Okay, there's a question here.
Yeah.
Thanks for your excellent talk.
Thank
So I noticed that you also use the phenotypic characterization to describe the behavior of an individual, and you actually extracted 4 decision.
Yeah.
Okay, so because I have seen some papers that they use maybe 40 to describe this behavior. So how do you extract these decisions, and how can you ensure that 4 decision is enough to accurately show the behavior of an individual?
Thank you for your question. And this is a very good question, because I also made this situation with other collaborators. They also asked this question. And I think that's because actually, yes, if we consider a very large scale problem, maybe we have actually like thousands of decision points. But actually, if we consider real world application, maybe we don't need that heuristic that perform different, but not very different. It's like if we have 1,000 heuristic and if we have 1,000 decision points and the 2 heuristic that maybe they only different at 2 decision points. Yes, they are different, but not very different. But in real world application, users prefer heuristic that perform quite different to each other to provide them alternatives. And give an example, it's like for color, we have normal green color, and we have light green, and we have dark green. But maybe we need a very different color, like yellow. So and another reason we only select 4 decision points and with 3 candidates is because we want to have a manageable QD map. If we consider a very large number of decision points, the map will be really large. Yeah, thank you.
Yeah, thank you.
Have time for more questions? Okay, I'm just going to check if there are any questions online. So while people are thinking of questions, I just have one question regarding your population size. It was 200. Sorry, not the population size, the number of generations. It was it was 200. How did you come to that? Did it take that many generations for it to actually converge, or was it through trial and error or by parameter tuning?
Yeah, usually actually previously I also do this topic and I only use like 50 as a generation. So use 50, we already can get a good solution. But because in this paper, it's more about analysis and we want to say how the map evolution. So if we use a large generation, we can say how the map evolution and how the map is correct in the end. Yeah.
Okay. Thank you.
Thank you.
Do we have, thank you.
Thank you for the nice talk. One question. So you have a diverse set of heuristics.
Yes.
Did you analyze to see if there's some regularity between the heuristics themselves? I mean, I understand they have different behaviors, but maybe they have some regularity, some subset of regularity within them that could be describing a more general rule, or this type of analysis it does not make sense.
Okay. Thank you for your question. Well, yes, in this paper, we didn't analyze the whether we have a general subtree can give a better generalization ability. But you are right that maybe we can further analyze the similarity, not only the difference between rules, and to find whether we can get some general rule can give a very good generalization ability. Yes, thank you for pointing that out. We might do that in the future. Okay.
Thank you. Let's thank our speaker again. Okay, and we now go on to our next speaker, who is Philippe Antis. Just and then I just want to share the screen. And if you do share the same code analysis, have a check here. Have a check here. You just need to put it in presentation mode. It's got to be in presentation mode first. Seems to be showing the notes. So you just go to present the notes. And you could make that bigger, and then share screen, and then disable the notes. But I can't see it here. You can use that. You can take it out from there.
Hi. Oh, hi, everyone. It's working. Perfect. All right. Hi, everyone. My name is Philippe Antis. I'm glad to be here, and I'm excited to share a paper I've written together with Dominik Sovania and Franz Rotlauf, which is called Transformer Semantic Genetic Programming for Symbolic Regression. First of all, let's start with a really simple example. We have a regression problem that consists of predicting the house price based on a house size. And there are some data samples, and the data is scaled between 0 and 1. And in a regression problem, all we want to do is to find a model that best describes the underlying data. So let's start with a simple model. So on the right side, we can see the syntactic representation or the genotype of the function f1. And on the left side, we can identify the curse of the function or its behavior. And that behavior is also called the semantics. And in symbolic regression, we can easily describe the semantics by just trying different input points. that span across the space of all possible inputs. For example, let's create such a semantic vector. We test it on small values, on medium ones, and on some larger ones, and the result is a semantic vector that describes the function. So let's have a look at another function f2. And at first glance, it's actually hard to tell if those functions are the same, but no, they're not the same. The size is now squared. And this small modification actually has a huge impact on its behavior, as we can see on the left side in the figure. So now the curse of the function is completely different. And that difference can be measured again with the semantics. So we use the same input points we already used for function f1, like the same small, like the same medium ones and the larger ones. And we also get a semantic vector again now. And now we can measure the distance between those vectors. So let us do that using the semantic distance. Oh, shifted below, but you can see that the semantic distance is 0.21. And this is actually a high value in the normalized setting. So let's conclude a small modification of the genotype of the functions can actually have a huge impact on the semantics. Let's have another example, function f3. And now it's really hard to tell if this is somehow semantically related to a function f1 or f2. But again, if we use the figure on the left side, we can plot it that it's basically quite similar. And this semantic similarity is also measured using the semantics and the semantic distance again. And now, again, shifted to, below, the distance is much smaller to function f1. So one can vice versa say that also large modifications of the genotype of function can have small effects. And such small effects are actually desirable during variation in an evolutionary process because we want to gradually evolve towards optimal model behavior. But as you can see here, it's sometimes hard to tell if the structures are somehow behave similar. So we set ourselves a difficult goal to solve in our paper. So we wanted to develop a search operator that guides the evolutionary search with semantically similar variations, but we want to create those variations independently of their structural representation. And that is difficult if you have a look here, because those functions are quite structurally different. So we need a powerful model, and for that task we used a transformer model, and we called our paper Transformer Semantic Genetic Programming, or short TSGP. So let me just introduce what TSGP does. So basically TSGP is a model-based variation operator that considers the semantics of functions in the variation process. And it consists of two phases. So the first phase is like a model building phase or pre-training phase, how you call it, where we train a problem-independent transformer model only once to learn semantic similarities between functions. After the model is aware of those semantic patterns, we can transfer the knowledge to unseen problems where it actually acts as a mutation operator that now generates offspring of high semantic similarity. So let's go into detail into model building. So the first step, what do we need first if we want to train a machine learning model? We need data. So lots of data in that case. We created lots of mathematical functions using GP, and GP solves noisy linear RSR problems, basically. And by doing that over and over again on randomly created linear RSR problems, we get a huge archive of functions that are diverse. And we can test the semantics again by just using some input cases for every function we generated. So on the right side, you can also see that. So we have input cases, we test our generated functions, and we get their semantics. And with those semantics, we can now search for similarities between the functions. So we're now acting in the semantic space where we search for high semantic similarity. So basically, it's a k-nearest neighborhood search. And so, for example, we do this k-nearest neighborhood search for every function in our data set. And so, for example, f1, the function f1 is semantically similar to function f2 because it has a small semantic distance, but it's also similar to function f3. And with this knowledge, we can actually build input-output pairs to learn or to train our transformer model. So f1 and f2 is now an input-output pair, which we can use in the subsequent step. So let's do that. Train a model. So we use the models now and the functions now and not the semantics anymore. We only use the semantics to detect semantic similarities. Now we're using the functions again. And the goal of the transformer model is now to predict a semantic similar function based on an input function and and semantic distance we measured in the step before. And this is done for every input-output pair we discovered in the previous step. So just let's sum it up real quickly. So it basically consists of 3 steps. First, we need a lot of data, functions, and their semantics. Then we search for similar behavior, use it in the semantic space, and build some input-output pairs. And we use those input-output pairs for model training. After the model is trained, we can basically use it as a mutation operator, where it creates for each function in the population a new function with similar semantics based on a desired semantic distance, which is kind of an hyperparameter we can use. For example, in GSGP, we also have like a mutation step. It's basically the same. And now the huge difference to other model-based approaches is that during the search, we are not building the model anymore. We just sample from it. And this is also visualized on the left side. So we provide an F1 input function, and the transformer model can generate ourselves a semantically similar function. Of course, we did some experiments. So let's go through that. So we introduced a small transformer, which is adapted from Vaswani et al., but only with 2 encoders and decoders. And we trained it on 5 million semantically similar function pairs, only for 8 epochs. We benchmarked our approach with standard GP, slim geometric GP, which is another novel method, which considers the semantics. Also, we used 2 model-based variation operators, deep symbolic regression and denoising autoencoder. We tested the benchmarks on 5 data sets. And here are the results, and the results look quite promising. So TSGP on the left side outperforms the other approaches on the majority of the evaluated data sets, especially on ERA, ESL, and LEV. And on those other data sets, TSGP gets a prediction quality somehow similar to standard GP. For example, on pollen, standard GP is the best, but actually there's not a huge difference between TSGP and standard GP. Whereas on Galaxy, slim GSGP performs the best. But the results are quite promising. That's because, so as a result, we also had a look at the convergence speed of our method. So we had a look at the training, on the training set. Oh, I hope you can see that. So the blue line is our approach, TSGP. The orange line is standard GP. The green one is slim GSGP. And the y-axis is the error MSE. And on the x-axis, we have the generations. And as you can see is that our approach, like TSGP, where it performs really good, also converges really quickly towards really good solutions. So only after 10 or 12 generations, we already could find some really good solutions. Whereas the convergence speed on pollen or Galaxy is somehow comparable. Of course, we also had a look at the size. So the size is basically the amount of nodes of the best individual. So the amount of nodes is on the y-axis, and axis again, the generations. The colors stay the same. So our approach is TSGP again. And those results are interesting because we achieved the best results on ERA, ESL, and LEV. And despite the fact that we have the best individuals, our approach produced smaller individuals than the slim GSGP. Yes, it's a little bit larger than standard GP, but we beat standard GP on most of the data sets as well. And on data sets where we performed similar to standard GP, we produced somehow similar, a little bit larger individuals than standard GP. Of course, we needed to validate our approach. So we needed to check if we actually can generate semantic similarities on unseen data sets. So that's why we introduced something like offspring similarity. Let me explain that real quickly. So during evolution, we have a parent individual and an offspring, and we can calculate their semantics. And again, we can compare those semantics and can measure how closely related those are. And by measuring this, we get an Euclidean distance, which is like the semantic distance again. The lower the value, the more semantically similar those offsprings are. And the first thing what you can notice is that standard GP often produces offspring, which is not semantically similar. That's can be seen at the 75th percentile of standard GP, which is always higher than the other approaches. But interestingly, our approach actually could learn during training what semantic similarity constitutes. So we actually learned what semantic similarity are because we could transfer those similarities to unseen data sets. We achieved on ERA, for example, ESL and LEV, the lowest distance, so the offspring are of the highest semantic similarity. Whereas on the data sets of from Galaxy and pollen, where we achieved comparable results to standard GP, the model kind of a little bit struggled to create those similarities. But overall, transfer learning worked. So we could transfer those semantics learned during the model building phase, which we only conducted once, to unseen data sets. And this is really interesting. So let's conclude. So what's, again, TSGP? TSGP is basically a model-based variation operator with a kind of transfer learning. So during the model building phase, TSGP learns patterns between semantically similar functions. And then we're able to transfer those patterns to unseen and unknown problems and can actually generate offspring of semantic similarity. Oh, I hope this QR code works. But yeah, nevertheless, so TSGP outperforms the baseline in prediction quality, especially on those cases where we could achieve the transfer learning, where we actually could produce offspring of high semantic similarity. So thank you. And I hope this QR code works. If it doesn't, okay, perfect. And if you have any questions, just ask me or write me an email, how you want. References.
Thank you for a very good presentation and excellent work. So I'm just going to open the floor for questions. Okay, there was one there, and then there.
Thanks for the nice talk. I have a question about the relationship between your training set and your test set. So if I understood you correctly, you used 5 million samples from a training set and they were all linear functions, is that right? And how does it matter how closely they are related between training and test set?
Yes. Yes, that's actually a good question. No, they're not linear functions. We just generated synthetically linear SR problems with a lot of noise, and then we applied GP to solve those problems. And during the run, GP creates a lot of functions that are not linear at all. There's also some non-linearities in there. And this is actually, if I can just switch to the backup slide, we also analyzed the functions that are evolved with our approach. And as you can see, there are a lot of backup functions. As you can see, the resulting functions are not linear at all. There are a lot of non-linearities in there. So yeah, I hope this answers your question.
So these are when you actually optimize, but the training set were linear functions, were they not?
No, they're not only linear functions. GP search is also for generates functions that are not linear.
Perhaps I can jump in. The two sets of functions have nothing in common. No? Though we have basically the test set, which they have not seen before. And for the training, that the original problems where we only use them to generate basically solutions to let a GP run. And this was linear functions, which was where we slowed noise in it. And then the GP, when trying to model these functions, it came up with a variety of different functions. But the purpose of this was just to get a variation of different functions that we can use the transformer to learn similarities between semantic properties, between semantically similar functions. No? That was the goal. In principle, the idea is you have seen these 5 million numbers that are you just generated. To really develop this, then we would basically build up a set of solutions where you throw in all solutions that you ever find, which are promising. You throw them there in these reservoir, and this you want use to train the model, no? to get a transformer model which better detects which solutions are semantically similar to each other. But of course, the semantics also then depends on the specific problem that you solve, because these 6 or 5, 6 different problems, they have different semantics. But nevertheless, although you trained really the model for these synthetically problems, where you said, okay, what is any reasonable stuff there? Still, you learn there helps you really to efficiently solve these unseen problems where you have seen results up.
There was one question here, and then one there, and then I'll.
Hi, thank you for the talk. It was very interesting. So you partially answered to my question that was, are you training the transformer for each data set? So you are training, no?
We only trained the model once. And then
you apply to different data set?
Yeah, yeah.
And how is possible if the semantics are different? Is where I get lost. Like a different problem has different semantic, no? Yeah, but for all the data set. Okay, how is the training time of the transformer?
The what?
The training time.
The training time. Aha, the training time.
Yeah.
I only trained for 1 day, I think.
Okay, and
So
that's
it was
it.
okay. That's it.
Okay,
Yeah.
perfect. Thank you.
Thank you. We can take one more question. I think that was the next person.
On one GPU, an old one.
Okay, it's a really quick question. So, what was the rationale for choosing the baseline methods and the 5 data sets? Because of course, 5 data sets is quite limited to draw a conclusion. And also I miss some big names in the baselines for the algorithms.
So regarding the first question, we chose the baselines because we wanted to have a baseline that is also semantically aware, like SlimGCP. And those other 2 baselines are actually also model-based variation operators. So that's why we chose them. For example, DSR or DAE. Regarding the data sets, as we started with this approach, we just wanted to test it on 1 dimension. So we had a look at PMLB, where we can find a lot of black box data sets, and we just basically chose a dimension where we have a lot of data sets available. But yes, of course, we need to. So our model currently works on a specific dimension, but we will extend this in an extension.
Okay, in fact, I agree with the choice of baselines, but it still would be useful to have one of the top performers of the SR bench to at least see how it compares with the top performance of symbolic regression that we have right now. Do you have any experience on that?
No, not yet. So those are 2. So we only also used like 50 generations. So those are small experiments on our bench. I think we have a lot of fitness evaluations available, but we did not conduct such experiments yet.
Okay, thank you.
Thank you very much. Okay, we'll just quickly check if there are questions online. I know there are a lot more questions. This was a very interesting talk that has stimulated a lot of discussion. So you can actually chat with the speaker during lunchtime after the session. But I just want to quickly check. No, we don't have any questions online. So let's give the speaker a round of applause again. Okay. Our next speaker needs no introduction to both the GP community and to Gecco. So Thomas is well known in the community, and his presentation is on the paper that has been given the Best Impact Award, which was measured over the past 10 years from presenting in Gecco in 2015. So I'll hand over to Thomas.
Full screen. I actually have no idea how to make this full screen. All right. Good morning, everyone. I guess good afternoon, everyone. My name is Tom Helmuth. I'm here to present the talk about the SIGEVO Impact Award. That was awarded to a paper that I wrote with my co-author Lee Spector, who unfortunately could not be here today, but I think he is here online. In this paper, we developed a set of benchmark problems for benchmarking program synthesis systems, specifically for genetic programming, but not limited to genetic programming. So these problems are general purpose and can be used for any type of program synthesis. I want to start by thanking SIGEVO for this award and thanking all of you who have used these benchmark problems in the last 10 years and hopefully made good use of them. So I want to start with a little history about how these benchmark problems came to be. Back in 2012 at Gecco, a large group of genetic programming researchers came together and said, the problems that we're using for benchmarking are not very effective, right? A lot of the benchmark problems that were being used were toy problems. These problems were small problems that were easy to solve for genetic programming, And so there's a big worry that those problems weren't necessarily representative of how we want to use GP in the real world. And so the lessons learned using them may not be useful. And so this first paper sort of set a challenge for the GP community to come together and develop sets of new benchmark problems that could better be used to develop GP. Later that year in GPEM, an article was published that gave some recommendations of some specific benchmark problems, but more generally, some recommendations of how to go about benchmarking GP systems. Now, one thing that this paper lacked was a set of benchmark problems for general purpose program synthesis. And so a few years later, actually in 2015, just up the road in Madrid, we published this paper that's receiving the award on the General Program Synthesis Benchmark Suite. This paper put together a set of 29 benchmark problems that were all taken from programming textbooks, specifically for introductory textbooks. And so these are problems that humans use when they're learning to program. And so we thought, well, if humans use these use these problems when they're learning how to program, perhaps we can show that GP can also learn and grow and improve by using similar problems. Now, as I said, these are general purpose program synthesis problems, and by that I mean they require a large number of data types. So everything from strings, integers, booleans, characters, to data structures that use those, like including vectors. They also require control flow, so loops or recursion and conditional execution. And finally, they require large instruction sets. So instead of the small instruction sets, like maybe 4 to 10 instructions, often used in something like symbolic regression, in order to solve these problems, you really needed a large general purpose instruction set that included dozens, if not hundreds, of different instructions. And so this sort of changes the shape of the search space compared to something like symbolic regression, where you have a much smaller instruction set. The other important thing I wanted to mention here is, like many GP systems, these programs are specified using input and output pairs. And so that means for a given set of inputs, you know what the desired outputs are. In other words, this is what you might call a supervised learning problem. And so just to give an example of one of the problems from this benchmark suite, the syllables problem says, given a particular string, count the number of vowels in that string. And so you can see how this problem would require you to use different data types, such as strings, characters, integers, probably booleans, as well as a control flow, such as looping over the string, conditionals on what are vowels and which characters are not, and so on and so forth. And so these were the initial set of results showing how we could benchmark using these problems. The actual results don't matter because this was 10 years ago and we've improved a lot since then. But what we did show is that we could use this set of problems to benchmark 3 different parent selection mechanisms. So we compared tournament selection, implicit fitness sharing, and lexicase selection, and showed that using these benchmarks, we could differentiate between those different parent selection methods. So this was sort of our first example use case of these as benchmarks. So I want to talk about how these problems have been used in the last 10 years. We now call this problem suite PSB1 because about 4 years ago, we published a second set of benchmark problems. About 200 studies have used this set of benchmark problems, and I want to lean heavily on some work by Dominic, Dirk, and Franz, who wrote a really nice paper a few years ago that looked at all of the evolutionary computation papers that have cited this work and showed some interesting sort of accumulated results based on that survey. And so I wanted to point out 2 things. These are borrowed directly from that paper. First of all, these benchmarks have been used in papers published at a variety of venues, most notably Gecco, so that's great, but also a variety of other genetic programming and evolutionary computation venues. Additionally, and again, I think this data is a little old, so there have been others since then, but many of the systems that have been used with these problems focus on stack-based GP, grammatical evolution, and grammar-based genetic programming, and linear GP. In fact, a few other studies since these results have come out have also used other types of genetic programming as well. And I'm not going to go through all of these examples, but I just wanted to put a list of different GP methods, different GP components that have been benchmarked using these problems, just to show sort of the breadth of where these have been used in developing and improving GP systems, as well as I know of at least 3 examples of non-evolutionary methods that have been used as program synthesis methods to solve these problems as benchmark problems as well. So this brings us to the present, and I want to talk a bit about where we are now with GP program synthesis so that we can think about where we should go heading forward. At this point, genetic programming has solved 26 of the 29 problems in our original benchmark suite. One of the other problems that GP hasn't solved has been solved by a non-evolutionary approach. So that really is interesting in that there's places where GP is not performing as well as another approach. The other 2 problems are, in retrospect, probably not good choices. These were problems that, for a variety of reasons, were very deceptive and not necessarily indicative of program synthesis. In 2021, one of my students and I published a second suite of benchmark problems that has 25 mostly harder problems than this original benchmark suite. The idea here is because genetic programming has improved so much on program synthesis, on these original benchmark problems, we want to make sure we keep moving the field forward and aren't just sort of stagnating to improve on a set of small specific problems. And so these newer problems I see as a stepping stone to developing larger and larger program synthesis solutions. Now, the good news is GP has improved, and we've seen many developments that have come out of using these problems for improving GP systems. The bad news is GP still tends to struggle on larger problems that require things like helper functions, modularity. And so I see this as a challenge of, I'm going to talk in a minute where we want GP to go in the future. The things that we should be focused on as we continue to develop our GP systems. So I want to now think about moving forward. What do we want GP for program synthesis to do? How does this compare? The elephant in the room is large language models. I want to talk more about how GP program synthesis compares to large language models. And think about, since this was a paper about benchmarking, how we should consider benchmarking in GP program synthesis moving forward. And so the first of these questions, I think the answer that I would give is still the same answer that I would have given 10 years ago, which is I see 2 different directions that GP program synthesis can provide useful applications. The first of these is in automating sort of either routine or even non-routine program generation. So specifically, we're talking about program generation based on examples, as I mentioned earlier, based on input and output examples. And so this is a place where I think GP still has room to grow. And the other place here is in solving problems that have never been solved before. And so genetic programming has always been thought of as a way of using evolution to develop creativity. And so I think there's certainly room here for using GP in general, but specifically for program synthesis to solve novel problems that have never been solved before. So I want to read this quote by John Koza. A wide variety of seemingly different problems from many different fields can be recast as requiring the discovery of a computer program that produces some desired output when presented with particular inputs. That is, many seemingly different problems can be reformulated as problems of program induction. So this was from John Koza's original GP book. And I think this still holds true today, right? That we want GP to be able to do things that humans have never conceived of before. Now, let's talk about large language models. I want to talk about some about the differences between GP and large language models. The first thing that I'd mention is that typically, we think of them using different specifications. When we're using a large language model to generate code, we typically give it a natural language description of the desired program, where in genetic programming, we typically give a series of input and output examples. And so I think we as a GP community can focus on applications where we have these sets of input and output examples and don't necessarily have say, an English language description of a program as places where GP can still be very competitive with large language models. There's obviously problems with large language model hallucination, where large language models sometimes say, here's a program that solves your problem, and it certainly does not. I've even seen places where it hallucinates instructions that don't exist in the programming language. And so we should think about what can GP do that large language models cannot. I really think this idea of generating programs based on examples is important. I think we can also think more about ensuring correctness. Large language models don't really give us any guarantees of correctness in the code that they generate. Most GP systems can't either, but if you generate a program that passes all of your training cases, you at least know that your program is doing the correct things for some set of inputs. And finally, I'd definitely like to encourage us to think about how do we use GP to solve problems that have never been solved before. Large language models are really good at taking ideas that have been done before and combining them or recasting them in different ways. But I don't know that large language models are necessarily good at being creative and coming up with new solutions to new problems that we otherwise have no way of solving. And so this is an area where I think GP could certainly shine in the future. And finally, we want to ask, how do we benchmark these ideas? Here, I actually have more questions than answers. We have these problems in GP of scaling GP to solving larger and larger problems. I think that's something that we're going to need to consider moving forward. And how do we solve this problem of developing modularity? Also, if we want to benchmark the ability of GP to solve novel problems, that's a lot trickier than benchmarking GP to solve problems that we know how to solve, right? If you know how to solve a problem, you can give correct input and output examples, and that's much easier to benchmark. If a problem has never been solved before, I don't know that that necessarily makes a good benchmark. However, we do need some sort of benchmarking in order to tell if a GP system is likely to be able to solve those novel problems. So I don't know exactly what this looks like. It might look something like the ARC prize, except for solving novel problems. But I'm not sure. And so I think there's a lot of room for innovation here in benchmarking. I developed this benchmark suite when I was a graduate student working on my PhD. For all the PhDs in the room, especially if you're looking for a project and you want to think about how do you help move the field forward, putting together a benchmark suite that handles some of these things can be an excellent way of helping contribute to the field. So to conclude, this suite of benchmark problems has been used to help develop GP systems over the last 10 years. And how we think about benchmarking GP and developing GP systems for program synthesis moving forward should keep these things in mind of what do we actually want these systems to do. Thank you very much.
Thank you very much for a very informative talk. Questions?
Hello, thank you for the talk. So I was wondering, what do you think about sharing the minimal instruction set to solve the PSB1 or PSB2 benchmarks? Because like I think in symbolic regression, at least this instruction set is minimal and everybody uses the same. So it's easy to compare each other between different algorithms.
Yes.
Whereas in PSB2, like everybody can implement their own instruction set, so I cannot compare with others, being fair.
Right. So this is a great question of how do we compare the use of instruction sets for solving these problems? And this is an especially hairy issue because different representations sort of are going to necessitate different types of instruction sets. There have been some efforts to think about how you get sort of a minimally comparable instruction sets. But yeah, I don't know that I have a good answer there. And it's certainly something that I could imagine good work coming out of is looking at solutions to these problems and thinking about what are the instructions that seem necessary for them and perhaps trying to generalize that across different representations. But I don't know that I have a great answer for now, and it's certainly something that could see good work.
Thanks for the great impactful work. I just want to mention a very small point about the LLM approach. I mean, of course, you can put it through just as much rigorous testing as you do with the GP ones. So that's just a minor point. But I think for me, the sort of future of this is to really fully embrace what LLMs can do. And they're brilliant at writing lots of code, right? And for generating the sort of large programs, well, actually, large programs, if they're well structured, just constitute lots of calls to smaller functions and so on. But I think as a community, I'd really encourage us to embrace games more as really challenging open-ended things. So if you have multi-agent games, then the challenge is to beat the other agents. And it's really incredibly open-ended. Whereas the benchmarks as we have them, most of these can really be solved by LLMs now, right? So to just a comment on that. Thanks.
Yeah, I agree. I think games are a wonderful problem area that we can use.
We have one.
This is also, hello? Yeah. This is also just a remark. I mean, when thinking about what GP can do and the LLMs maybe not so well, is the topic of genetic improvement, which is quite closely linked to your topic. Not fully synthesis, but replacing parts of existing programs. Yeah.
Agreed.
I wanted to mention this. Bill is not here, but
yeah.
Commented on that.
I haven't worked directly in program improvement, but I think that's certainly another area where that's clearly very similar and related to synthesis from scratch.
Okay. We have a question from Bill online. So should a forward-looking benchmark be fair, solving a new problem better than doing 1% better than a problem already solved?
Can I read the question? I don't know. Should a forward-looking benchmark be fair, solving a new problem better than doing 1% better than a problem already solved? So as in trying to benchmark or create problems that we have never solved. I mean, I have a hard time conceptualizing how we benchmark solving an unsolved problem. I think it's certainly a great idea to think about, but I don't know exactly what that looks like.
Thank you. Let's thank our speaker, congratulate our speaker one last time. Okay, so our last talk, but not the least talk for the session, is by Quentin Vashi, and I'll hand over to him.
Oh, you can't go back.
Just to. Okay. Hello everyone, I'm Katavashi. I'm gonna present our work. I'm sure all of you are really hungry, especially after all this amazing talks. I'll try to be really fast. What I'm gonna present is an algorithm that we propose to assess continuous multi-action problem of reinforcement learning, where for now genetic programming has not been able to achieve really high results, especially when the number of action is really high. For that, we present the Maple algorithm. Oh, it's actually, okay, well, it's fine. Maple stands for multi-action program through linear evolution. And to be quick about our contribution, it's an algorithm that we build on linear genetic programming, and we base the evolution on Tangle program graph. We're going to detail Tangle program graph after, because I know not everybody knows about it. Quickly about our results, we were able to outperform the GP state-of-the-art on the Gecco suite. And compared to the state-of-the-art of the deep reinforcement learning, we were able to equal and sometimes to outperform also some of the algorithm on 4 out of 6 environments. For the other features that we have with this algorithm, we have, usually have with GP, we have a strong interpretability, but this time we have it for each of the actions that we are taking. And also, even if we are not going to detail this, we have really small complexity compared to what we have usually with deep reinforcement learning. Okay, so quickly, what are the Gecco environment? These are environment of reinforcement learning that look like this. Oh, the video doesn't work. That's a shame. So normally you should see it move, but it doesn't work. These are mostly locomotion tasks where the agent is moving to the right. Normally we are seeing actually the behavior of the Maple agent moving, but anyway. Most of them are environment with multiple actions, so it's really complicated to learn because you have a lot of action to take at each step. We just kept the inverted pendulum at the top left with only one action to show that our algorithm is also able to work on only one action, where it's basically just some linear genetic programming working. Okay, so for this presentation, we are going to focus on the end because it will be easier to focus on only one environment instead of doing all the environment. So it's something that looks like this, where you have some action and some observation. The action to take are the different torques that you will apply on all the joints of the end, and the observation vector is a list of position and velocity information about the end. Okay, so the initial building block of our algorithm is the linear genetic programming. So it's basically a box with some registers that are all initialized to 0, and some inputs that are the information about the environment, so the observation space. The execution are some instructions that evolve through the genetic process, and it takes some register and some inputs to compute some instructions that are initially random but evolve through the genetic process. And in the end, you just output the first register of your program. So this is what you do normally with classical GP, but in our case, because we have to take 8 actions, obviously one register is not enough. So what we do is that we output the 8 registers that we need to take all the action. So in the end, we have an agent that looks like this, and that is taking all the action. So this has been used on Gecco before, and this reach efficient solution for environment with a small number of action, but when you scale with a lot of action like the end, it struggles to scale. And the supposed reason we have is that you have all the thinking process and all the actions that are taken by a single little program, and this struggle a lot to scale. So to try to compensate that, we use the Tangle program graph algorithm, where you basically take a lot of linear genetic program. Some program you can see have only one wet square. It means that this is program with only one output, and the other one are program with multiple output, which are the classic action program that we just saw. The one with only one output are what we will call context program, and it's programs that will help to know which path of the graph to take. So the way it works is that we will start at the top of the graph, and we will execute each of the program on the edges. And thanks to the observation space, each program will output a value that we will call a bid. And this is basically the confidence the program is thinking of how we should take his path or no. So usually we will have one program that will lead, and we will continue his path, so we could reach another team, and we continue the same processes where we have different values that are outputted. And in the end, we usually finish by reaching an action program that is taking again the action as for linear genetic programming. So This is really efficient for subtask division. Like if you are learning a game like Pac-Man, for example, where sometimes you have to run away from the ghost and sometimes you have to chase the ghost, it's really good because the teams and the program are able to indicate which part of the environment you are in. Unfortunately for Gecco, it was still struggling where the number of action was improving. And the supposed reason, again, is that even if this time the reflection process is divided into the context program, you still have one program that is taking all the action. So we thought about it and we tried to thought how we could keep this subtask division that we have, but doing it for the action level, because this is where we're struggling. And the solution we came up with is a much simpler structure where you have only one program per action taking all, like one program responsible of one action. And by doing that, it actually reached much better results. So we just simplified with the action values that it's taking, and we are going to explore a little bit the evolution process that we are using. So initially, we have the initialization, like in all algorithm. And so we initialize a certain number of agents, and we initialize each agent with some edges. We actually figure out that having only a certain number of edges that is not the number of action is actually working better. Like in the end, we have 8 action, and actually having 8 edges is not the best way of working because it seems that leaving only small number of edges at the beginning is easier to make the learning process efficient. So after that, we have the evaluation where we just evaluate our agent on the Gecco environment, and we have the selection where we will eliminate some agent. Then we have the mutation process that starts that we copied from the Tangle program graph because it's an algorithm inspired from it. So we start by duplicating one of the surviving agent, and then we will do the first mutation that is to remove some edges. So we will randomly take an edges and delete it from this new agent. After that, we have the adding of edges, where we don't really have crossover in this algorithm, but it's kind of some crossover because to add some edges, we will copy some edges from other pre-existing agents. So in a way, we are taking some already existing material. After that, we have some switching, which is a new mutation compared to Tangle program graph, where we switch some action by keeping the same program, so it adds more diversity in the agent. And in the end, we have the mutation of the program, apparently, mutation of the program, where we do some classic LGP mutation on the program, like switching some lines, mutating some line, etc. And also we can mutate some action value, as long as it's not an action value already used. So we do that for a lot of agents, and in the end, we have a whole new population that is created, and we will put these processes to have a whole new result. Okay. So how does the Maple algorithm scale on the end environment? Here we have the LGP algorithm, Maple, TPG, and MATPG that I'm going to talk about just after. So already we can see that Maple is able to really scale really well compared to LGP and TPG, which is really nice, especially compared to TPG because we have a much smaller complexity by the fact that we have a small graph. And also we have this MATPG algorithm that I haven't presented yet. I'm going to present it right now. It's basically a hybrid version that we created between the TPG and the Maple agent, where we took our TPG from before and we replaced the action by some Maple agent to try to improve the results. So I'm not going to detail exactly how it works because we don't really have time. And also, as you can see, it didn't really improve the results. We reach basically the same results and we just have more complexity. Also, with that, we have the deep reinforcement learning state of the art that on this environment still reach much better results than us. So if we look at all the environments, you can see that sometimes Maple, like usually Maple is always almost always better than TPG and LGP. And compared to deep reinforcement learning, sometimes it's at the same level, sometimes a bit lower, sometimes a bit higher. One of the environments that we are not able to learn for now is the humanoid. If you have seen the paper before, you can see that the results are a little bit different. It's because like 1 month ago, we figured out that there was a bug in our program. So the claims are not different, just the results are a little bit different. Okay, so on average, deep reinforcement learning is still better. However, Maple is able to offer some other advantages. And one of them, as usual with GP, is interpretability. So I know that interpretability is always a tricky subject to talk about. So I took a definition from the IBM website that I'm just going to read. So interpretability is about transparency, allowing user to comprehend the model architecture, the feature it uses, and how it combines them to deliver prediction. And what we are really interested here is the transparency and the feature it chooses and how it combines them to deliver the prediction. So when you use deep reinforcement learning, you know the architecture, but you don't really know what's happening inside. While when you are using Maple, we really know what's happening. We could say it's a white box model, although I'm not going to say, like, I put some, yeah, I'm not completely sure. We could say it's a white box model. But yeah, we have this model, and also we can know exactly which action are responsible of what in the graph. And normally we can look at the best behavior, but the video is still not working, I guess. So normally we could say that we have a variable with behavior, even if the results are lower than the state-of-the-art deep reinforcement learning. But anyway, if we look at one of the program in detail for this best agent on the end, we can see exactly what's happening inside. And from that, this is the actual programs we are using. That the agent is using, and we can have the equation of that behavior. That is basically what state, what part of the state are used for making the action. And we can do that for all the action. So some of them are much more complicated than others, but in general, it's still pretty small, and we're able to do it at the action level, so it's really interesting. We can do some interpretability if we look directly at the end of what part of the state it's using. So we can say, for example, for this action 2, that the action 2 here is a multiplication of the angular velocity of the angle between the back right links and the Z orientation of the torso. So I don't really know what it means, and that's not really the point here. I don't want really to explain why it's doing that, but what I want to show is that we know exactly what it's doing. So it's really important for reliability. And we can do the same for this action 4, where action 4 is the difference between, again, this angular velocity of the angle between the back right links and the X orientation of the torso. Okay. So we still have a feature selection that is effectively done, which is really good. And this time we're able to do it at the action level. So it's really interesting because if we scale on much, much larger reinforcement learning environment, we could have also some really interesting analysis to do. And if we do a little bit of explainability, we try to run our agent on some environment to collect some correlation between action and state. And we're able to have the correlation. I don't know if you're able to see, but we have the correlation between all the action and all the state features. And this is really interesting to do. This is something that you can do with deep reinforcement learning, but you can only do it with all the state compared to each action. And here, thanks to the feature selection, we can do it from a small number of states compared to all action. And some things are interesting. For example, the 3 dark red square here at almost 0.9 are the state 28, which is this angular velocity between the back right links. I don't know why this angular velocity, it's really important because it doesn't seem to be important, but apparently it's really, really important for taking the actions. So in summary, we propose a Maple algorithm that outperforms the GP state-of-the-art on the mediocre suite. And also it allows an effective interpretability, again, at the action level. We implemented all that with the JJIT framework, which is a C++ framework initially built for the Tangle program graph, but we improved it with the Maple algorithm. We have 100% coverage, so it's really nice. And everything is open source, and you can find everything on the GitHub link just here. And for future works, what we are interested in is to use some crossover, because right now crossover are not used in Maple. One, like, as I said, like we use a little bit crossover by the mutation process, but we don't have full crossover, which makes like, because we took the mutation process from TPG, in TPG it would be really weird to use crossover because the agents are all completely different, while here they all look alike, so it would make sense to use some crossover. Also, we actually tried a little bit, and for now it's not really working. If you are GPTP, you might have seen that. And what path we are working on right now is to improve also the diversity, which will be linked to the crossover also, to try to improve both at the same time. And finally, one thing that we lose with Maple compared to Tangle program graph is the emergence, where TPG have, I didn't describe how TPG evolved, but we have a dynamic emergence in TPG, which is really interesting. And we would like to work on again here on the Maple algorithm. Thank you very much for your attention. And if you have any question, feel free to ask.
There are 2 comments online, but I just want to see if there are any questions on the floor first.
Thank you, Contam, for the presentation. I just have a question about destructiveness of your operations in the graph. I'm wondering if you study this somehow in this framework, because you do like 4 operations: a subtraction, addition of graphs, switching, and mutation. So did you maybe like see how far the new solutions are from the parent solutions?
So, sorry, I didn't understand.
You're creating like new solutions by performing 4 operations on them after cloning them. I'm wondering if you study how destructive these perturbations are, or whether the new solutions are very far away from the parent or close by.
Yeah, that's in like the diversity part that we really need to explore, because like we just part of the algorithm and it led to really good results, and we were really happy about that, and it was really nice. And now we need to build a much more stronger structure about that to identify the diversity and how the new agents are really different from the parents. I hope it answers the question.
Thank you. Yes.
We have time for one more question from the floor, otherwise we'll go to the comments online. Anyone has a burning question? Okay, so quickly, so Lee basically is looking at, you can have a look at him. Yeah. Let's look at Gilbert first, and we'll go back to Lee. So I wonder if the bidding behavior of TGP could be done instead of introducing conditional instructions into the main LGP program.
The bidding behavior of TGP could be done. Oh, okay. Maybe like the issue with using TPG in that case that I didn't really explore is that when we use TPG, because we have a whole graph to evolve, it's like the reason we suppose it's not really working is that we don't have enough, we really need to focus on the mutation and the action, and it's really hard to say to the graph to focus on this part of the mutation. So this is why we try, initially we just wanted to use this MA TPGs that I presented, but we end up just using a maple that was much more smaller and much more usable.
So Lee's comment was related to ongoing
No,
discussion.
excuse me, can you hear me?
It's not relevant to your talk, so.
Thank you very much.
Let's thank our speaker once again. Just a reminder to please vote on the best paper for the session as well. Thank you. Sorry, just an announcement. We have a meeting in here now. So, sorry, one moment, just an announcement. There is a meeting in here now. So if you want to discuss further, if you can please move out and discuss, please. Thank you.